Hi class, I'm taking one more day to recover. Hopefully I'll be back on campus on Monday. So here's a lecture to go for the last half of today's class. I hope by the time you watch this lecture you'll have finished your test and you did super with it. See you on Monday. In this problem, we have an insulating sphere. It has radius r and net charge q uniformly distributed throughout its volume. So what that bit here means, uniformly distributed throughout its volume, means that this is a ball or sphere of charge, and it has some extra positive charge, and all of those positive charges are evenly spread out everywhere. They're not more concentrated in one place than any other. We'd like to find an expression for the electric field both inside the sphere and outside the sphere. To do that, we're going to use Gauss's law. So we'll write down Gauss's law. The net electric flux is the integral of E dot dA, so the integral of the electric field over the area of some closed surface, and that's equal to the net charge enclosed by the surface divided by the constant epsilon naught. So we're going to need to draw a Gaussian surface. Let's make sure we understand our electric field. When we have a sphere of charge, our electric field is radially outwards. So I've redrawn my sphere down here. I'm going to draw my electric field vectors. So radially outwards. My arrows aren't perfect, but hopefully you're getting the idea here. So there's my electric field. To pick a Gaussian surface that makes this integral easy to do, we have to take advantage of the symmetry. And to do that, we generally pick a Gaussian surface that looks like our object. So we're going to pick a Gaussian surface that's a sphere. Part A asks for the electric field inside the sphere. So let's draw our Gaussian surface as a sphere inside of our charged object. Gaussian surface is a sphere with radius r. Turns out our approach here is going to be suitable for if r is inside or outside, but let's work through it with r inside. So as we do our integral, we're going to want to find the integral of E dot dA. So let's write down that expression. The integral of E dot dA, the scalar product with the element of area of our Gaussian surface. So let's draw our dA. That's a little bit of area on our Gaussian surface. So we'll just pick one of those little bits of area. I'll just shade it in. That's my dA. The direction of dA is radially outwards. Okay, I've drawn my dA. So my integral of E dot dA, that's a scalar product. It means the magnitude of E times the magnitude of dA times the cosine of the angle between E and dA. Here's where the advantage of the symmetry comes in. Area is radially out, electric field is radially out. The angle between those two things is 0. So that's the integral of E times dA times cosine 0. And of course, cosine 0 is equal to 1. Okay, next bit. Because of the radial symmetry, as long as this is a sphere, so it has a constant radius r, the electric field is the same everywhere on this surface because we're the same distance from the center everywhere on this surface. That means the magnitude of E is constant. It can come out front of the integral. The integral of dA is just the area A of our Gaussian surface. Okay, so now this expression is true for any r. Okay, whether r is inside or outside. So now what we've done is we've dealt with the integral portion of our Gauss's law. The net electric flux can be given by E times 4 pi r squared when we have spherical symmetry. On our next slide, we'll start to deal with Q inside. Now we have to deal with Q in. So first let's make sure we understand what Q in means. This is the amount of charge enclosed by the Gaussian surface. That's a really important concept, and that one can be tricky to figure out sometimes. So our Gaussian surface, we've decided, is a sphere with radius r less than r. It's a sphere somewhere inside of our charged object, so it's this sphere right here. Let's remember that the charge is evenly distributed throughout this entire sphere. So now here's the first question to make sure you understand. How much charge is inside this blue sphere I've drawn? Is it all of the charge Q, none of the charge Q, or some of the charge? Okay, let's think about that for a moment. Since our charge is uniformly distributed, there's some near the surface, there's some near the middle, our Gaussian surface only encloses part of the total sphere, so it only has part of the total charge. So Q in equals fraction of total charge. Hopefully that makes sense. Okay, now we have to remember, how are we going to figure out that charge? Well, our net charge is going to be the charge density. And since we have a three-dimensional object, we're going to have to do the charge density times the volume. So we're using volume charge density here now. So density, volume charge density, it has a symbol of rho, and it's the total charge divided by the total volume. Our expression for volume here means of the Gaussian surface. I'll just write GS for Gaussian surface. The volume of a Gaussian surface is the volume of the sphere with radius little r, 4/3 times pi times r cubed. Make sure we label that well on our diagram. So our little Gaussian surface has radius lowercase r. Our charged sphere has radius uppercase r. Okay, so the net charge inside this volume is whatever the charge density times the volume. And the charge density is given by the total charge divided by the total volume. Let's put those things together. Q in equals our density, total charge divided by total volume, times the volume of the Gaussian surface, 4/3 pi times little r cubed. That means that our net charge inside equals, let's see what cancels. 4/3 cancels, pi cancels. So we're left with our total charge Q times the little radius cubed divided by the big radius cubed. Okay, now we have an expression for the integral of E dot dA, the net flux. We have an expression for the charge inside. Let's put those together and see what we get. Okay, let's put it all together. The net electric flux is the integral of E dot dA. That's E times 4 pi r squared. Equals Q enclosed divided by epsilon naught. Our Q enclosed is given by Q times the radius of our Gaussian sphere cubed divided by the total radius cubed. And that has to be divided by epsilon naught. Let's solve for our electric field value E. So that's going to be 1 over 4 pi epsilon naught. You can write that as K if you prefer. Times Q. We have r cubed on this side, r squared on this side. Divide both sides by r squared. You're left with an r. And then we still have r cubed in our denominator. So this is the electric field inside the Gaussian surface, or inside our sphere of charge. So on a Gaussian surface with radius r smaller than the radius of the sphere of charge. What we see here is that the electric field is linear. It gets bigger linearly proportional to r as we get to the surface of our insulating sphere. For part B of the problem, what is the electric field a distance r from the center of the sphere where r is greater than r? So now we want the electric field outside. We begin with Gauss's law. Net electric flux equals the integral of E dot dA equals Q enclosed by our Gaussian surface divided by epsilon naught. Quick reminder, our electric field is radially outwards. Never hurts to draw that again. We have to pick a new Gaussian surface. This time for our Gaussian surface, let's pick our Gaussian surface as a sphere with radius bigger than the radius of our insulating sphere. So our Gaussian surface is going to be a sphere outside. So our Gaussian surface, GS, is a sphere with radius bigger than the radius of our insulating sphere. Okay, let's start to deal with our terms of Gauss's law. From before, If we have radial symmetry, the integral of E dot dA is equal to E times 4 pi r squared. Okay, we don't need to go through that process before. We don't have to go through that process again. We've already shown it once, and once is enough in any given problem. But we'll put in a reminder that we already did that in part A, and that result came from spherical symmetry. What about our Q in? Okay, Q in means how much charge is enclosed by our Gaussian surface. So let's look at our blue line, and don't overthink this answer. And let's ask how much charge is inside this Gaussian surface. Well, let's ask what charged object is inside the Gaussian surface. That would be our charged sphere. Now let's ask, is all of the sphere inside, some of the sphere, or none of the sphere? Well, this time all of the sphere is inside. So our charge enclosed is the total charge because all of the sphere is inside. Okay, let's put all this together. So our net electric flux is equal to E times 4 pi times r squared, where r is bigger than the radius of our insulating sphere. That's equal to our net charge divided by epsilon naught. Let's solve for our electric field. E is 1 over 4 pi epsilon naught. You can write that as k if you prefer, times our total charge divided by r squared, and this is for r greater than the radius of the sphere. Okay, so this is our electric field magnitude outside of the sphere. We've already drawn in our diagram that the direction is radially outwards. What we see when we're outside of our sphere of charge is that the electric field looks just like the electric field due to a point charge. All right, for part C, we'll just do a plot of the electric field. So for part C, we want to draw a graph of the electric field. As a reminder, our answer for part A is that the electric field was K times Q times position divided by the radius of the sphere cubed. For part B, the electric field was K times Q over position squared. For both of them, the direction is radially outwards. Now if we want to draw our graph, let's just put one point of interest on our graph, which is r equals the radius of the sphere. So when we're inside the sphere, we increase from 0 to some maximum value. That's a linear relationship. So inside it's linear. The maximum value we get is right here at the top. At this value, the electric field is 1 over 4 pi epsilon naught times q times r cubed. Oops, sorry, not r cubed, r squared. You get this result if you put r equals r in either this expression or this expression. So that's our maximum electric field. That happens right at the surface of the sphere. Once we get outside of the sphere, it decreases to 0 as r gets very big. So outside it goes as 1 over r squared, and as r gets very large, the electric field goes to 0. So there's a plot of the electric field as a function of position.
For a homework question now, I'll have you repeat the problem with a conducting sphere. I feel like this is going to be pretty straightforward, so I'll go ahead and post the answer, but I'm not going to make a video. Get in touch if you have any questions.